say we have 2 qubits and they're in this state. Actually a completely general state, W amplitude on 0, 0, X amplitude on 0, 1, Y amplitude on 1, 0, Z amplitude on 1, 1. And I'll call this 4D vector S. And we can draw this picture. We have W, X, Y, Z. So 0, 0, 0, 1, 1, 0, 1, 1. A is going up and down, B is going left and right. And say we do extract B. Now, this is exactly what we talked about in the first half of the lecture. So we know that the probability of seeing the outcome B is 0. Okay, it's the total squared amplitude on the B equals 0 side, which is W squared plus Y squared. And the probability of seeing B equals 1 is X squared plus Z squared. Now, I want to just show you another way you can work this out. That's pleasant. It's nice to start with S and factor it. Now, it doesn't look like you can factor it necessarily, but you just kind of want to group. If you know you're going to be doing extract B, you maybe want to kind of group things together based on the B value. So what I mean is we can say that S factors, in some sense, as something tensor 0 plus something tensor 1. And the something here is, W0 plus Y1, and then X0 plus Z1. Okay, so if you expand this out, you should get this. And you can kind of see, right, this is like the left edge in the picture, which is like the B equals 0 edge. And this is like the right edge. It's like the B equals 1 edge. And let me call this 1 qubit state ket, I don't know, L for left. Let me call this 1 qubit state ket R for right. And please note that these are unnormalized states, because the squared length of L is W squared plus Y squared, and the squared length for R is X squared plus Z squared. And actually, those two quantities should remind you of what's above. So just write this. These are unnormalized. And in fact, the squared length of L, just the dot product of L with itself, is W squared plus Y squared. And the squared length of R is X squared plus Z squared. And these are also the probabilities here. Okay, so let me just end on this, and then I'll do a little calculation next time. So if A and B are in the state L tensor 0 plus R tensor 1, then the probability that when you extract, B of getting 0 is just the squared length of L. And if this happens, the new unnormalized state of A is just L. And similarly, the chance that we get 1 is the length of this R vector squared, and the new state of A is R. Okay, so this is like maybe like a nice algebraic way to like, I don't know, take states that are in this form and understand this extracting one qubit that we saw in the first half of the lecture. Before we get to that, I want to like wrap up some calculation I was in the middle of doing at the end of the last lecture. It wasn't like very important or anything, but it was just trying to illustrate some of the computations we were doing, and it'll warm us up for today too. So let's just get back to that briefly. We mentioned we had two qubits A and B in some state, any state, which we're going to assume is normalized. And we're eventually going to be concerned with doing a measurement or an extract operation on B. So it's good to write the state like this, where we kind of factored out the B part. Any state can be written in this form. So we've done that. So in general, if the state's amplitudes are W, X, Y, and Z on the four basic states, then you can write it like this. And you see here that like on the B equals 0 part, we have WY. That's what we're calling this vector, cat L. And on the B equals 1 part, that's like this edge, we have this one qubit state. Well, no, I shouldn't say state, but this one qubit vector, XZ. Okay, I shouldn't say state because these L's and R's, cat L and cat L, are not necessarily unit vectors. In fact, they're probably not unit vectors, because in general, the sum of the squares of these four numbers is 1 if the state's normalized. But they have some meaning. So actually, if you look at the dot product of cat L with itself, which from a geometric point of view is like the squared length of this vector, then that's W squared plus Y squared. And we also know that this is the probability that if you were to measure or extract B, that you would see the outcome 0. Okay, we saw that last time. If you just measure the qubit B, you see outcome 0 with probability W squared plus Y squared, and you see outcome 1 with probability X squared plus Z squared. Okay, and we also saw that, you know, if you do this extract operation and outcome 0 does occur, then the remaining qubit A is left in some state. And what is its state? It's just this vector. It's just L. Now that's, as we said, like an unnormalized state, but that's fine. You can normalize it if you want. There's a similar story for if the measurement outcome is 1, which occurs with probability equal to X squared plus Z squared, which is the length of this vector squared. Okay, so I did all that so that we could do this little calculation. Let's say if you're starting with this 2 qubit state, which I called S, if we do this little 2 instruction program, 1, extract B, 2, do some unitary U on A. Okay, so this measures B, and then only qubit A is left, and then we could do some unitary operation, like a rotation or something on A. What is the result? Well, there's 2 cases. You have to like split into cases based on what the outcome was for the extract operation. So, I don't know, case 0, one might say, is that with probability equal to the length of this cat L squared, you get 0 in line 1. And then the new state of, a normalized state of A is cat L. And then we do U on that. So the final state of A, and this is unnormalized. That's okay. State of A is just a U applied to cat L. And case 1 is, well, that the outcome of the extract is 1. So I'll just write like this with probability length of cat R squared. The outcome for the extract operation is 1. And then the final unnormalized state of A is U applied to cat R. Okay, you might think like, okay, that's fine. That's a okay calculation. But I bring it up because I want to now also just illustrate for you what would happen if you did these 2 operations in the other order. So I'm literally going to analyze the exact same code, but with opposite order. So I'll say on the other hand, say we start from this state, this 2 qubit state S again. So first I'll do the instruction U on A, and then I'll do extract on B. Okay, what is the result? Well, let's first figure out what happens after line 1. Well, we talked about this last time. If you have 2 qubits, and now you're doing an operation on only one of them, you have to remember how that works. But this is also a very convenient way to write the state if you're planning on doing just this. We saw last time that the new state is like U applied to ket L, tensor 0, plus U applied to ket R, tensor 1. Okay. So it works like as you might guess. And now we can think about what happens after line 2. And again, there's 2 cases, which we can again call case 0 and case 1. So now we're doing extract B on this state. And we saw last time, and also from this same calculation, that the probability that we see outcome 0 is like the length of this squared. Okay, this is still a normalized state, so it's the squared length of this. Okay, but now we remember this is U is a unitary operation. That means it doesn't change the lengths of vectors. And that's true even if they're not necessarily unit vectors, which ket L is not. It still doesn't change its length. So this is also equal to the length of L squared. And that's nice. That's using unitariness because it's the same probability as here. So this is again the probability that you'll see outcome 0 when you measure B. And if this happens, I'm not writing this fully properly, but if this does happen, the new state of A is just this. It's a new unnormalized state, but that's okay. Okay, and again, that matches up with this. So case 0 is exactly the same. And maybe I won't write it, but like I'll just say it in words. Case 1 is the same as on the other board again. Okay, that's because from this state, if you do extract on the second qubit B, this is the B part here, the probability of seeing 1 is the squared length of this, U times ket R, and the length of that is the same as the length of R. So we again get the length of R squared, and again, this is the state that A will be in if you do see measurement outcome 1. Okay, so the point of this computation is to show you that these 2 boxed algorithms give you the same result. And this is a good fact to know. It has some both mathematical content and physical content even. Let me write the conclusion here. Which is that operations done on separate sets of qubits can be done in either order, and it's equivalent. So it can equivalently be reordered. And this is something that we saw very early on in this class when you think of operations as meaning unitaries, like these qubit manipulation operators. We checked that on some homework or something. And here I'm illustrating to you that it continues to be true if not only you're talking about unitaries, but also these special kind of qubit operations, measurements or extractions. So it's still true that as long as they're on like separate sets of qubits, you can reorder them, you can actually parallelize them. It doesn't matter which temporal order you do them in, you'll get the same result. So this is very useful mathematically. It means, you can do either this computation or this computation, whichever you prefer, when you look at this code and say like, oh, these are acting on separate sets of qubits, so I can pick my favorite order. But there's an important physical principle at play here too, which you can think about by remembering that, like, in the end, this is like mathematical instructions for how to do a physical operation on physical objects, and like, the qubit A is actually some physical object, like an electron or something, and the qubit B is also some physical object, like an electron or something. And, once they get into this state, cat S, it's perfectly possible to, like, move them far apart. And it's very common in these stories for, like, qubit A to be owned by, like, a person called Alice, and qubit B to be owned by a person called Bob. And Alice can, like, that once they get into this state, cat S, like, Alice can pick up the electron A and, like, start walking away. I mean, if she's careful about it. And similarly, Bob with the electron B, if they're careful about it, they can move them far apart, and they'll still be in this joint state as long as they're not disturbed. So Alice can take A, like, all the way back to her lab or her house, or the moon, and Bob can also similarly take his qubit very far away, and if they're careful, they'll still be in this joint state. And because of this, like, a physicist will actually know that this somehow must be true, because, and I'm stepping into territory, I'm not an expert on physics, special relativity dictates that, like, for sufficiently far apart, like physically far apart objects, like, it doesn't even necessarily make sense to ask which of two events happened first, like an event that happened physically here and physically here. Like, did this come before this one in time? Like, it depends on, like, the observer's reference frame. So if they're, like, farther apart than the speed of, light can, get between them, you can't distinguish which ones happened first. And therefore, you kind of know, for physics reasons, you kind of have to get the same results if you do these in different orders, because, like, who's to say, like, which one actually happened first? Okay, but, like, happily, we just check with math that indeed you get the same results. Okay, any questions? Those are going to be very interesting to us, because now we're going to see some, like, fun things. I mean, I'm going to show you, ultimately what I'm going to show you, like teleportation and stuff, it's just going to be like, 5 lines of quantum code, and on its own it might not seem so impressive, but we're always going to be imagining that, like, remember, like, we could do this with Alice having this qubit way over here and Bob having this qubit way over there, and it looks like more impressive when you think of it this way.